So what I have here is my phospholipid bilayer, and you can see that these are the same kind of models that I had at the end of the last video. I've got my negatively charged phosphate head because of all the oxygens that are present in there, and I've got my hydrophobic phospholipid tails. Now they happen to arrange themselves into what we call here a phospholipid bilayer. A bilayer meaning two layers. And it's really so that these hydrophobic hydrophobic fatty acid tails are here in the middle, which allows for the hydrophilic heads to be on the outside, which is where we would find lots of water molecules. Now let me slide this all down just a little bit so you can actually see the water molecules that I'm bringing into the screen. So we've got some water molecules. Let's say that we've got one, two, okay, we're going to put 5 here, right? Okay, so let's say that we've got, I'm going to label this side, and you know that this would be extended in this direction. This phospholipid bilayer would be extended in that direction, and it would be extended in this direction. What I'm actually going to do is replace my phospholipid bilayer here with a different model that looks like this. It doesn't have the negative charged indicator on it, but we know that each of these has a negative charge in it. But before I do that, I want to point out that this water is uneven, right? So we've got, let's say that this is the inside of the cell, and this is the outside of the cell. Okay? So this is the extracellular fluid, this is the intracellular fluid. And there's more water on the inside. There are 3 waters on the inside and only 2 waters on the outside. So what we're going to see happen is that some of these water molecules are going to actually move out. But the problem is that water doesn't mix with hydrophobic things. And here in the middle of this phospholipid bilayer is a hydrophobic region. And so we know that water is small and it's polar, and because of its small size, it can actually force itself pretty quickly through and in between the phospholipids. Remember, well, I haven't mentioned this, but the phospholipids are actually not connected in any way. They just happen to be associated next to each other because they like to create this hydrophobic region for their fatty acid tails. Oftentimes we'd find cholesterol, I don't have that in this model, but we'd find cholesterol embedded in this hydrophobic region as another lipid that helps the structural integrity of this phospholipid bilayer. Additionally, some of these fatty acid tails will be unsaturated instead of saturated fatty acids, which causes them to bend, like basically kick a leg out, which prevents the tight package of this phospholipid bilayer, but what it allows is the fluidity of the phospholipids. So these phospholipids are never stuck in place. They're constantly moving, and for that reason we call it the fluid mosaic model, and I would urge you to write that down, the fluid mosaic model. Fluid meaning it's moving, and mosaic meaning it's made of lots of parts. So far, all I've mentioned is phospholipids and cholesterol. So, water has a hard time moving across the membrane, although it can move between the phospholipids. We know it needs a protein to do so. So I'm going to add a protein in my next model. So I'm going to go ahead and move these guys out of my model. Leave my water in place. So I'm going to move these out of view. I'm going to put my new phospholipid bilayer in place, but I'm going to open it up and put a protein in. Okay, so I'm going to add I think it goes in like this. Oh, I've got my phospholipid in the wrong way. That's the problem. Alright, so then I've got my protein here embedded. So now I've got my phospholipids, I've got a channel protein, and I've got my water molecules that will be able to travel. And because I have 3 on one side, these 3 are going to, one of these 3 is going to move through this protein channel, which allows it to move in a region that is not hydrophobic like the fatty acid tails of my phospholipids. I'm going to put one here just so you know what I'm talking about. Okay? Put a second one over here. Okay, so it's going to be able to travel through and try to find that magic E word that we call equilibrium. The problem is, with the few that I pick, now I've got 3 on one side and 2 on the other, so maybe another one's going to come through and move back. And we call that a dynamic equilibrium. Dynamic means it's changing, equilibrium and balance. So it's always finding balance, but because the molecules are always in random motion, unless they're 0 degrees Kelvin, they will be moving back and forth across this membrane. What we won't find in most situations is all of the water molecules traveling in one direction against the gradient unless there's some other force that's forcing it to do that. Because this would be not at an equilibrium. We have 5 on this side and 0 on the outside of the cell. So that would never exist unless there's something that's driving it. But we call this process osmosis. And yeah, let me move to the other screen and define that process for you. Alright, so the process that I'm talking about is osmosis, which is the movement of water across a membrane to reach equilibrium. Now, equilibrium in concentration. So it needs about the same amount of stuff on either side, but if we have different, basically it's just trying to even out the concentration or the density of that molecule rather than the number of that molecule. So cross membrane to reach equilibrium, and so basically it moves from high concentration, and this is my abbreviation for concentration, from high concentration to low concentration of water. But let's say that we have other stuff mixed in that water. What it actually does is it moves from low concentration to high concentration of solutes. So it moves in the opposite direction of the solutes, and really that's what water will follow. So let's say that we moved, let's say here's my phospholipid bilayer, and we moved lots of chloride ions out. Well, water is going to move out to help reach an equilibrium of concentration, so water will follow. Chloride doesn't move, water doesn't move, and that has other impacts on the other side of the membrane. Now, I will point out that the protein that, just as a factoid, which might come in handy, which will come in handy, that protein that it travels through is called an aquaporin. An aquaporin. And this is the protein. That's actually the structure of this protein won a Nobel Prize a few years back. And it helps to explain how water can move across that membrane really, really quickly. Because it has a special pore to allow it to do that. Now, I would be remiss if I didn't mention this because I forgot. I was so excited about the model that I forgot about a process that we call simple diffusion. And some things, simple diffusion, so some things, let me get my handwriting a little better here. Some things can move through the bilayer on their own. They don't need a protein to do so. And oftentimes these things are nonpolar and small. So the examples would be oxygen, which is just 2 oxygen atoms, not something really large which we're getting ready to talk about, or carbon dioxide, So again, this is not much bigger than an oxygen molecule. So these things are really small. They are non-polar. They don't have a charge, and so they can move very quickly. What I just talked about was H2O, which is also very small, but it's polar. So it doesn't move very quickly across the membrane. It really needs that protein to do so. And when it's water, we call it osmosis, but really this is a special case. It's a special case of facilitated diffusion. And facilitated diffusion is a special type of diffusion that gets help from a certain protein. In the case of osmosis, it gets the help from that protein called aquaporin. But it's not always aquaporin, and it's not always water. And so let's go back to the other model, and I'll show you what protein is being involved, what is being used for facilitated diffusion. Actually, scratch that. I need to go back to the osmosis thing because there's a new idea that I forgot to mention. And maybe it's not a new idea, but it's about this idea of hypotonic, hypertonic, and isotonic. And so when we have, let me scoot this around just a little bit. Okay, so when we have lots of water on one side and it rushes to the other side, so let's say we've got, I'm going to put a few more water molecules here. So we've got a lot of water inside the cell, and it's being forced out because, let's say there's only one water molecule on this side. And we've got a lot more water molecules here on the inside of the cell. Well, there's going to be this natural drive for these water molecules to go out. And because there is less water and probably more solute, that's what this kind of represented here. Less water, which means more solute, and here's more water and less solute. This water is going to naturally flow without any extra energy as a form of passive transport. By the way, the other forms of passive transport are simple diffusion and facilitated diffusion. But this water floods out through this protein. And if this protein did not, let's say it was blocked or wasn't there at all, this water would be stuck on one side. But what ends up happening is when you put something in an environment with lots of solute, that we would then call I'm not going to write this here, but I want you to write this in your diagram if you're jotting this down, which I would be. This is called a hypotonic solution. Scratch that. Hypertonic. Sorry. That's really confusing. Hypertonic solution. That means there's more solute, less water. Hyper means more. Tonic refers to tonicity of the amount of solute. So this is a hypertonic solution. And in this hypertonic solution, water is going to be driven to it to dilute the tonicity, to make it less concentrated. So let's see how much. I have 1 over here, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 water molecules on this side. So to be at equilibrium, 5 water molecules are going to go through this protein. 1, 2, 3, 4, 5. So I've got 6 on the outside and 6 left on the inside here. So that's what's going to be left, and that doesn't mean that now this protein's closed, so some water molecule can get through, but now there's a higher concentration on this side, so water's going to be driven back because they're bumping into each other, and they're going to constantly be moving in dynamic equilibrium. Write down dynamic equilibrium. So that's there's a lot going on there, and when it's hypertonic, that water is driven to it. But now there's less water on the inside, and so that cell has shrunken. It's gotten much smaller. If the opposite was true, let's say that we put a cell in an environment that has a lot more water outside of it than inside of it, so that there's more solute inside of that cell than outside, then water is going to rush in, and we would label this cell as hypertonic, right? Except we don't call the cell hypertonic. We call the environment that it's in, the outside environment. And so then this outside environment has more water and less solute, we would call hypotonic. That means there's less solute, and that water is going to be driven in the other direction into the cell, which causes the cell to expand maybe even causing the cell membrane to burst open, and that might be bad news. So shriveling up or bursting would be bad news, and that's why some organisms work really well in marine environments and they can't be transferred to freshwater environments, and vice versa. Putting a freshwater frog into the ocean would cause it to shrivel up because water would come out of it to dilute the ocean water. And if you put a marine jellyfish into a freshwater environment, it would inflate with water and burst. That's why that sad experiment that kids do all the time, which is very unfortunate, of putting salt on a slug causes it to dehydrate. The water comes out of the slug to find equilibrium with the salty environment that a child has put that poor slug into. So that's hypertonic and hypotonic, and isotonic means that there's the same solute concentration inside and outside the cell. Okay, so that's osmosis. Let me talk very quickly about other types of facilitated diffusion, especially for things that are much bigger than water. So I'm going to remove my water molecules from my screen here. I'm also going to remove this aquaporin as best as I can without breaking my model. I think it's stuck on a sticker. Okay, and so now what I'm going to do is put my see if I can get this to fit right. So this is my glucose transporter. My glucose transporter. Okay. So here I've got my glucose transporter, and I still got the inside and outside of my cell labeled there. I'm going to take some of my glucose molecules. So look how big those glucose molecules are compared to water. This is that C6H12O6 molecule, and I'm going to go ahead and put 4 of them outside and only 1 on the inside. So what's naturally going to happen according to this protein that's in this cell membrane is that I'm going to close it like this because this is what it normally sits in its resting state. And when this glucose comes in, comes into the protein then, by interacting with that glucose, changes its shape and allows the glucose through. And now I've got 2 on the inside and 3 on the outside. So another one's going to be driven through. And when it releases, it goes back to its normal form. It does not require energy to do so. So this is a form of passive transport. And it's going to do this until it finds equilibrium, which is really cool. But then now I've got 3 on this side, so 1 will come back and it will go back and forth, trying to reach equilibrium. And that is a different form of facilitated transport. But this molecule, glucose, is way too big to fit between the phospholipids, so it needs its own protein channels. What's really cool is that this glucose, once it goes in, let's say it's coming through your bloodstream and goes to some of your cells are going to use this protein to import these glucose molecules into the bloodstream, and then they will find their way to the mitochondria to be processed. Before getting to the mitochondria, they will be processed in the cytoplasm by glycolysis. So here they are in the cytoplasm, and they'll get broken down into the pyruvates in glycolysis, and if oxygen is present, if oxygen has already diffused through or will diffuse through this phospholipid bilayer, it will go through the rest of aerobic respiration of Krebs and the electron transport chain. And you know what happens if there isn't oxygen. So that is facilitated diffusion. So I'm going to set up the active transport video now, but I see this one's 20 minutes, so I'm going to stop this one and start another one for active transport.